Hello everyone, how are you doing? Today we're going to start talking about our first mathematical model that is used in decision-making theory. As we said before, we have several mathematical models that can be used to represent any data set out that can be used to they can help to solve the problem and help us to take the optimal or the best decision. The models that we're going to introduce today is what we call regression models. Some of you may have heard about regression before, some of you haven't, so in all cases we're going to, we'll start the subject from the beginning. So let's start with what is regression analysis, when are regression models specifically used in a decision-making process. All regression models are used to represent the relationship between quantitative variables. In its simplest form, a regression model, or what we call simple linear regression model, is used to represent the relationship between two quantitative variables. One of them is the independent variable, and usually this is denoted by x. The other one is the dependent variable, and it is usually denoted by y. In other cases, sometimes we need to study the relationship between several independent variables and one dependent variable. So it's like we're going to find what is the effect of many variables. Okay, so we have like many x's and only one y. This is what we call multiple regression models. Now, why do we use regression models? So specifically, as we said, to represent the relationship between, in its simplest form, two quantitative variables. So as this is what we're going to start, we're going to start talking about simple linear regression models. So now I have one independent variable, which is denoted by x, and we need to study the relationship of the effect of this variable on one dependent variable, which is y. And as we said, both should be quantitative. This is the first step to represent the relationship, and it is represented by an equation, by a linear equation that we're going to discuss in a moment. The second aim or the second target when in regression analysis is to use this equation to predict the values of the force of the dependent variable based on some known values for the independent one. As we said, the variable that we need to predict is the dependent one, or sometimes it is called response variable. So sometimes you use this word response variable instead of dependent variable. Okay, and the value of this variable, as we said, depends on the values of the independent variable. So the dependent variable or response variable is denoted by y. The independent variable is denoted by x. And the independent variable, sometimes in some of the studies, some of the books or textbook, will find it called the explanatory variable or predictor variable. So we use the independent to predict the dependent one. Okay. As you see in the slide, the dependent variable will be equal to an equation in the independent variable. Let's start from the beginning. Now, if I have a data set in which I have two quantitative variables and I need to figure is there a relationship, because I cannot talk about a regression model or a regression equation to be predicted unless I'm sure that there is some kind of relationship between these two variables. To figure if there is a relationship between two quantitative variables, we use a simple graph called a scatter diagram or a scatter plot. So the scatter plot is designed to represent this relationship and to figure if there is a relation, yes or no. Usually, if you have a graph paper and you want to draw, you have two axes, the x-axis and the y-axis. So the x-axis or the horizontal axis will be the axis on which you will represent the values of the independent variable x, and the y-axis, which is the vertical one, will be used to represent on which we're going to represent the values of the dependent variable. So as you see, the independent variable is plotted on the x-axis and the dependent variable is plotted on the y-axis. If you look at this slide or these figures represent what we call a scatter diagram. So now how do we plot these points? These points are plotted by, on the x-axis, we put the values of x using a suitable scale. And on the y-axis, we put the values of y by using a suitable scale. And then we plot the points. So for example, let's say we're talking about a value of x that is 2 and a value of y that is 5. So now it's like I have a point with two coordinates. The x coordinate is 2 and the y coordinate is 5. So I simply, on my sketch or on my graph paper, I plot the point with an x coordinate of 2 and a y coordinate of 5. For another couple of values, let's say x was equal to 5 and y is equal to 15. So I will plot a point with an x coordinate of 5 and y coordinate of 15. And I keep doing this, putting the points, and I will find that I will have a sketch like one of the sketches that we see on the slides here. Now, if you look at the slide and at the sketch A, you will find that the point we have like a general shape, okay, in which you can imagine that you can draw a straight line. This line will have a positive slope. Now, if you look at B, you will find also that the points here have, on the average, a general shape that can be represented by a line with a positive slope. And C also, still, all the points are can be joined by one straight line. So usually we say this is a full linear relationship. Now, if you look at the other three, figure number D, you will find that there is a general shape still that is linear and that has a negative slope. E, the same thing. D, E and T, F. So it's D, E, and F. D, E, and F, all of them are different scatter diagrams or different scatter plots that represent a linear relationship, a relationship between x and y that is what is called negative relationship. What is meant by negative relationship? It simply means that whenever x increases, y decreases. On the other hand, A, B, and C represent relationships that are positive, which means that whenever x increases, y decreases. Usually from the scatter diagram, the first thing that you can remark is the direction of the relation. So it's clear that for the figures A, B, and C, the relation is a positive one. For the figures D, E, and F, the relation is negative. Now, the second thing we usually like to know about the relationship between the two variables is the strength of the relation. From a scatter diagram, it's not that easy because this depends on lots of things. I may look at a figure and think that this is a strong relation. Someone else can tell that it's not that strong, it could be a bit weaker. But usually, as generally speaking, we can say that whenever the points are very dispersed on the sketch, this means that the relation is not that strong. It tends to be weak a bit. But if the points are so closer to each other, we say this is an indication for a stronger relationship. In addition to the scatter diagram, in statistics, we have measures that can help us to figure the direction, both direction and strength of a linear relationship between two quantitative variables, which is what we call the coefficient of correlation, or sometimes people call it correlation coefficient. And this is what we're going to talk about now. So the correlation coefficient is a measure that can help us to indicate the direction and the strength of the relationship between two quantitative variables. The coefficient of correlation, or the correlation coefficient is usually denoted by R, small case letter, and the value of R is always between -1 and +1. So when the value of R is negative, this is an indication that the relation that exists between X and Y is a negative relationship. If it is positive, this is an indication that the relation is a positive one. So if you look at the number line represented here, you will find that these are the three special cases for the values of R. If R is equal to -1, this is an indication of a strong negative linear relationship. If it's on the other hand +1, this is an indication of a strong positive linear relationship. If it's equal to 0, this is an indication of no linear relationship, of course. Now, what about if it is not equal to neither 0, positive, or -1? So the rule says if R is positive, which means that the relation is a positive one. So when the value of R is closer to 1, this is an indication of a strong relationship. When it's closer to 0, this is an indication of a weak relationship. So let's put some kind of small branch marks on this. So let's say that in the interval between 0 and 1, if R is equal to half, this means that we have what we call a moderate relationship. If R is larger than half, then the positive relationship is strong. If it is smaller than half, then this is an indication that the positive relationship is weak. On the other hand, if R is negative, which means that R is between -1 and 0. If R is equal to -half, this is an indication that the relationship is a negative moderate relationship. Okay, so whenever it is -half, you have a negative and moderate. So when R is between -1 and -half, yeah, it's closer to -1. Okay, this means that the relation is negative and strong. When it is between -half and 0, this is an indication of a negative weak relationship. Now let's put a rule here to deal with this. Let's assume, for example, that we calculated R for a data set and R was equal to 0.83, okay, which means that R is positive. So this is an indication of a positive relationship to start with. And since the value is larger than half, then this is a positive, strong relationship. Now let's give another example. On the other hand, let's say that R is equal to -0.83. Since it is negative, it's a negative relationship. Regardless of the sign, you can look at the value of the number itself. It's 0.83. Since this is larger than half, then you can say that this is a negative, strong relationship. So usually if you calculate the value of R, which is given, for us, the rule will be, you will be given the value, or you will be given anything to help you to indicate, and you will not be asked to calculate R, because as we're going to see in the next coming slide, we need a lot of calculation, and you won't be asked to do these calculations. The most important thing is to know how to interpret the value for R. And if you are given a value of R to represent the relationship between two variables, you need to know how to comment on this, how interpret the value. So you will look at two things. You look at the sign. If it's positive, you say positive relation. If it's negative, you say negative relation. And then in step 2, you look at the value. If the value is larger than half, it is strong. If it's smaller than half, it is weak. If it's half, it will be simply moderate. And this is what I told you. Actually, to calculate R, you will use this formula. Okay. طبعا it's a long formula, it's complicated, it is simply given to you just to have an idea. Okay, but you won't be asked to do this calculation, and this is what you're going to see in the coming slide. Let's look at an example just to show you the calculations that we do. But as I said before, you are not asked to calculate the value of R. In this example, we're talking about data that represent the revenue of car rental companies in the United States for a recent year. So here we have a number of companies, A, B, C, D, E, and F. So we have 6 companies, and we have the number of cars they rent. These are rental companies. So 63, 29, and so on. Now, what is meant by cars in 10,000? This means that this number 63, okay, is originally, if you have to multiply by 10,000, so it will be 630,000. Okay, this is what is meant by in 10,000. يعني the number given should be multiplied by 10,000. Here 1 and 4 zeros. Okay, why do we do this? Because this is easier. Instead of like the whole number of zeros, we put 1 unit of measurement, which is 10,000 in this case. The revenue is measured in $billion. يعني this first number 7 is originally $7 billion. First step, usually when we have a data set like this, is to draw the diagram. So as I told you, on X, we're going to put the cars in $10,000, in 10,000, sorry. So we have the numbers here using a scale, convenient scale. On the other hand, the revenue on Y, it is in billions. So let's go back, to the data. So here we have the first point, the second point, and so on. So we plot the points, and X coordinates the value of X, and Y coordinates the value of Y. Now, as you see, we're talking about the number of cars rented and the revenue. So which one depends on the other? It is clear that revenue depends on the number of cars. That's why the number of cars rented will be the X, and the revenue will be Y. So from what we see on the scatter diagram, looking at the point, there is a general shape that we can talk about, indicating that we have a positive relationship between the number of cars rented and the revenue. To compute the correlation coefficient, this is what we need. But still, I'm going to emphasize on what I said in the beginning. You are not asked to do this calculation. This is simply an example to show you how the calculations are done, but you won't be asked to do this. So usually we start by computing x times y, x squared, y squared, get the sums, and substitute in the formula. Okay, this is the most important part, which is now if R is given to be equal to 0.9982 or 0.98, this means that this relationship is positive since it has a positive sign, and it is strong since the value of R is larger than half. So we have a strong positive relationship between the number of car rented and the revenue. Let's take another example. AAA Construction renovates old homes. Managers have found that the dollar value of renovation work is dependent on the area payroll. what is meant by this data? So we have this this construction company, and the construction company, okay, as I thought about that, the volume of renovation, okay, depends on the area payroll. Yeah, it depends on the salary they pay for the workers. Okay, so the renovation of the company, which is represented by the sales. So the sales is measured in hundred thousands. Okay. They think that these sales depend on the area payroll, yani on the wages given or the salaries given to the workers. The payrolls of the workers' salaries in total طبعا is represented by 100 million. Okay. So for example, for the first case of sales اللي هي 6 means in 100,000 يعني originally it was 600,000 sales, okay, come from a payroll of $300 million. Now for the second value that we have here, what is this 8? This 8 is originally 800,000 sales for the company come from a payroll or a total wages, total salaries of the workers that is $400,000 and so on. So let's explain the third one برضه still to clarify if it's not clear for everyone. What is this 9? This 9 is to represent that 900,000 sales came to the company when the workers took $600 million. Okay, so these are the sales, and these sales depend on the payroll, how the wages, how the salary that the workers take from this country. Usually, if I want to study the relationship between these two variables, let's start first. Which one will be the X and which one will be the Y? Now, he said that the volume of renovation is dependent on the area payroll. Even this means that the sales, it depends on the payroll, which is X. Okay, so the sales of the company depends on the salaries given to the employees of the workers. So our X is the payroll and Y is the sales. Now, if I want to plot the scatter plot, so the first point will have an X coordinate of 3 and a Y coordinate of 6. Okay, so I plot a point. The second point has an X coordinate of 4 and a Y coordinate of 8. I put another point. The third point will have an X coordinate of 6 and a Y coordinate of 9, and I plot a third point. The fourth point will have an X coordinate of 4, a Y coordinate of 5, and so on. If you do this, you will find that this is the figure you will get. So now, if I look at the scatter diagram, I can think about I can draw a line, and this line will have a positive slope. So that's an indication of a positive relationship between the payroll and the company sales. Okay, which means that when the salaries of the payroll of the company increase, okay, we're expecting the sales to increase also. Now, for this company, calculated to be equal to 0.83, and this is typically what will be given in your exams, in your assignments. You will not be asked to calculate all figures, but you will be asked to interpret this value. What is meant by in the AAA construction company example, R is equal to 0.83. So what we need to say is simply this indicates that the relationship between the local payroll of the company and its sales is a strong, of course, positive relationship. It is positive, okay, which means this is positive. The value is larger than this is the indication of a strong positive relationship. Now the second step after we presented the relation, how we interpreted the relation between the two variables is to determine the equation of the regression line. Okay, the regression line is usually called the line of best fit. Now, why is it called the line of best fit? Imagine this is the scatter diagram we have. Now looking at this scatter diagram, it is clear that the relationship is a positive one. It could be strong or weak. What we care for is that it is on the average a relationship, and this is what is important for us. Now the idea is, on this sketch, I can draw many lines, okay, that join some of the points. Every line you see there are some of the points joined there. But the idea is, and I need to pick only one of these lines. Basically, if you think about which line will be the best one, that's why you call it the line of best fit, the line that best fits this data set is, and logically speaking, we simply can say that the line on which I can represent the majority of a large, or I can think about the line on which I can represent a large number of points. Okay, which is logically speaking correct. Now, but what if I had like 2 or 3 lines with the same number of points? Let's say, for example, 10 points on 2 lines. Still, I have to pick one of them. Now, let's say it in the simplest way, actually to compare between 2 lines, take the one with the best, what we call the best fit line or best line of fit. We can say simply, we're going to look now, in addition to looking at the points on the line, I can look at the points scattered around the line. Okay, so the lines that have the smallest distance around this. We have the smallest scatter around it, of the smallest variation. Okay, so the lines that have more points closer to it than the other one will be a better line. And actually, this is that we're going to use. Usually this is the relationship that can be represented in statistics between x the independent one and y the dependent one. So y is equal to beta naught plus beta 1x plus error, okay, or what we call the residual. This error is represents the distance between every point on the scatter diagram and the line. Sometimes the points are over the line, sometimes the points are below the line. But usually this distance between every point and the line is what we call the error or the residual. Now, the line that is used to predict the relationship between x and y is based on different data set, because usually in data set it is never related to the population but to the set. So the relation that we're going to use to predict the sign of regression is y equals to b naught plus b1x. And y we had a hat. That's why we call it y hat equal to b naught plus b1x. So for us, x is the independent variable, and y hat is what we call the predicted value of y. B naught is the y-intercept, it is your, b1 is the slope. So as I said before, the line of best fit will be the line, okay, for which this distance, the distance like d1, d2, and d3, the distance between the point and the line is the smallest. So actually what we can do is, when I look at this distance, okay, so actually if I have a first value for x here, okay, so for this value of x I can have two values of y. One that is called the observed value. The observed value is the one that we already have on the scatter diagram, and one that is called the predicted value. This is the value that we have on the line. So actually for every x I can have two y's. One, this is the observed value. The observed value is simply the value of y that is in my original data set, what's called observed. This is the data collected. The y hat is the value I can predict using the equation of the line that I have calculated. Sometimes this distance is positive, in some other times this distance is negative. This distance is what we call the error or residual. The line of best fit is the line for which the sum of the squares of these distances of these residual is the minimum. Let's explain it كده أو try to clarify the thing in an easier way or a simpler way. As we said, the line of best fit is the line for which all of the distance that you see on the sketch here, D1, D2, D3, D4, some of them are positive, some of them are negative, some of them, like the one that relates to this point, okay, will be 0. طبعا if all the points are on the line, this is the best thing. But usually, this is the theoretic thing that never happens. In practice, we must have the line with some points on it, some points below it, and some points above it. So we have some distances, and these distances are what we call the error or residual. So sometimes this error will be positive and sometimes will be negative. Based on what? Based on the definition of the error. The error is the difference between the observed y, which is the y given in the original data set, and what we call the predicted y, اللي هي y hat, given by the equation of the regression line that we're going to calculate. وطبعا, as I'm going to tell you in a moment, you will not be asked to calculate the equation, but you will be given the equation and your role will be to interpret the values given in the equation. So as we said, the line of best fit is simply the line for which the sum of the squares of these distances, which are the errors, is the smallest one, is the minimum or the smallest one. Okay, these are our notation. So y is the observed value, y hat is the predicted value from the line, and this notation epsilon represents the error. So the error for any value xi, okay, is equal to the corresponding y, or observed, minus the predicted. Epsilon is y minus y hat. If the observed اللي هي y is larger than y hat, the error will be positive. If the observed اللي هي y is smaller than the predicted اللي هي y is smaller than y hat, the error will be negative. So let's go back now to our example. In the AAA construction, okay, we had y to represent the sales and x to represent the payroll. Okay, so the line that we have chosen or that we have drawn on the sketch, on the scatter diagram, to remember, is the one that minimizes the error. As we said, the error is denoted by our epsilon, and it is calculated by the difference between the observed value given in the data minus the predicted one, which is calculated from the equation that so in the simple regression, in the simple linear regression model, y hat it will be naught plus b1. Usually to calculate this equation, how to estimate this equation, you need to calculate b naught and b1. Okay, b1 is calculated by the formula we see here, and b naught is calculated by the other one. Okay, which is y hat y bar minus b1 xy and mean of y minus b1 mean of x. And as I said before, still this part of your knowledge, but you will not be asked to calculate either b naught or b1, but simply let's show you the calculations that you need to do. So in this case, you have x and y, where we have to calculate x minus x bar squared, x minus x bar times y minus y bar. And then substitute in these formulas to get b1 and b naught. So now the important thing is the last equation we have here. Based on the calculations, y hat is equal to 2 plus 1.25x. Okay, now the idea is, as I said, you will not be asked to do these calculations. Okay, all you will be asked to do is, you will be given. So let's start with, if this example was given to you in an assignment or in a quiz or an exam, you will give it. You may be given the data, but actually you will be given this equation. So let's say start by, let's say that we have the AAA company, and here are the data simply to show what is the problem, and then you are given this equation. Now your role will be to interpret the value 2 or the number 2 and the value of the slope اللي هي 1.25. Okay, so the other way to say this equation, how to read this equation, is to say that the sales اللي هي y is equal to 2 plus 1.25 times the payroll. Now, if you are asked, if the payroll next year is $600 million, what are the predicted sales? And as if you remember, this is what we said in the beginning, that regression models are actually used to predict some unknown values of the dependent variable. So now, if the payroll next year is 600 million, which means that if X is equal to 600 million, what is the predicted value for the sales? In my equation, I have to substitute the payroll or the X by the value. If you remember, we said that payroll is measured in billions. Billions اللي هي 100 billions. Okay, so what we're going to do is to replace X by 6. Now this you substitute X. You will not be substituting X but 600 million. Why? Because in the we said the values are in billions for the payroll. In 100, sorry, it was in 100 millions. Yes, in 100 millions. Okay. Billions, correct. So we're going simply to divide this number by 100 millions. Now divided by 1 billion, which means that X is equal to 6. So I will replace X by 6 in the equation and get the corresponding value of Y. Y is equal to 9.5. And it was measured in 100,000. The sales were measured in 100,000. If I have to multiply 9.5 by 100,000, this will give me $950,000. Okay, so this is one of the things that you need to be careful about. Whenever you are given a data set, you have to look at the unit of measurement of both X and Y. According to this, if for example X was given in dollars, خلاص, يبقى the number that is given for you for X to use to predict the value of y will be replaced or substituted in the equation as it is. But in our example, x was given in 100 millions. Okay, so now I need to replace the value of x to be put in 100 millions. Since it was 600 million, يبقى I will divide by 100 million, يبقى I will get x equal to 6. Okay, so I will replace x by 6. But y was measured in 10,000. يبقى I have to multiply the value of y that I have calculated اللي هي 9.5 multiplied by 10,000. So I will get 950 y. Excuse me. So this is our equation now for the other example. Now let's start with let's move to the other example simply to show you what you will get. The first example, okay, it was written to show you how calculations are done and how to use the equation in predictions. Now let's go back to the car rental company's example in which we had the data about the number of cars rented and the revenue of the sales of the company. So we said that the sales of the company depends on the number of cars rented. Okay, so you are given the data and now you are given the equation. And this is typically what you will be given. Okay, so y hat is equal to 0.4 plus 0.126x. These were the data. Cars were measured in 10,000. So x is measured in 10,000. And the revenue of the company is measured in billions. Okay, this is example in billions, yes. The other one for the triple A was 100,000. Okay. Now let's look at what is given here. Let me look at the equation. Y hat equals to 0.4 plus 0.106x. In this equation, we have two numbers, or two constants that are very important. B naught, which is 0.4, this is what we call the parameters. And the slope, اللي هو B1, which is 0.106. Actually, the most important parameter in the regression line equation is the slope, اللي هو B1. Why? Because the slope actually is the indicator for the relationship between the dependent variable and the independent variable. Okay? Now, how are we going to interpret the value of B1 here, 4.106? Actually, the slope has many interpretations. In mathematics or in algebra, usually if you talk to a mathematician and ask him, how are you going to talk about what is the slope for you? You will look at the slope and say this is positive, which means that there is a positive relationship between the two variables, and the line has a positive slope, so it will look like this. It goes okay from down to up to the going right up, okay, increasing. Increases y increase. Okay, mathematically this is correct. But for us to use this to interpret this slope and the slope of regression line, what do we need from this? Okay, it indicates a positive relationship since it is positive. And this is the common part between the coefficient of correlation and the slope of the regression line. Both have the same direction. Okay, so if you know R, which we already did, we have R equal to 0.98, which means that there is a relationship, a positive relationship. It was positive regardless of the value. Since R is positive, we are expecting to have B1 as positive. If B1 is negative, so R should be negative. Yeah, both have the same sign, okay, indicating the same direction for the relation between X and Y. Now let's see how I'm going to interpret the slope. Usually the slope will indicate what we call the marginal change in Y, okay, relatively to X, which means what? Which means that every time X increases by 1 unit, Y increases by the value of B1. In the general equation, how do we interpret B1, اللي هو slope of the equation? When B1 is positive, this is an indication that whenever X increases by 1 unit, Y will increase by the amount of B1. If B1 is negative, this is an indication that whenever X increases by 1 unit, Y will decrease by the amount of B1. Let's see in our example. What is the unit measurement of X? We know that X is measured in 10,000, okay? Which means that for every increase of 10,000 cars, we expect Y, which is the revenue, to increase by 0.106 billions. Let me repeat this. Generally speaking, we said B1 is negative, which is the case here. Then, whenever X increases by 1, then Y increases by the value of B1. Now, in our problem, or in our exercise here, the one of X is 10,000, 10,000 cars. Okay? And the one of Y is $1 billion. So this is where the unit of measurement is important whenever you interpret the value of the slope and carbon intercept. So actually what we can say is, for every increase, instead of saying increase, you can say what? For every additional 10,000 cars rented. صح? Since X represents the number of cars rented. Okay? Or for an increase in the number of cars rented by 10,000 cars. Okay? So every time, okay, for every additional 10,000 cars rented, or if the number of cars rented increases by 10,000, we expect the revenue to increase by this amount of B1, 0.106. And remember that unit of measurement of Y was the billion. So it should be 0.106 billion dollars. So now I can write a full interpretation by saying that for every additional 10,000 cars rented, the revenue is expected to increase by $2.106 billion. Now, if you are asked to use the equation of the regression line to predict the income of a car rental agency that has 200,000 automobiles, what should we do? Okay, when I have X to be 200,000, I know that X is measured in 10,000. Okay, so if I want to substitute a value in the equation, I won't substitute 200,000. I have to divide this number by 10,000, which means that I will substitute X by 20. So substituting in the equation X by 20, this will give me Y to be equal to 2.52. That's it. We're not done. Because Y is measured in millions. So what we're going to do is to write down that if a rental agency have 200,000 automobiles, the revenue will be on the average approximately equal to 2.52 what, as we said, billion dollars. Excuse me. Now, if I want to go back and think of the interpretation of the y-intercept, if you think about it, the y-intercept is simply the value of y whenever x is equal to 0. In our example, x equal to 0 means what? Means that if no cars are rented, correct? So I can say that if no cars are rented, then we expect the revenue to be equal to the value of B naught, برضه $billion, and so on. Now, so basically, this is how you can interpret the linear relationship between the two variables. Now let's talk about what are the assumptions of the simple linear regression model. So actually, the relationship between the two variables should be linear, okay? And the values of the independent variable are not random. Only the error is the random variable. It changes. Okay, that are independent, and the errors are normally distributed to the mean of 0 and the constant variance, and they are not related to each other. Now let's start with why do we need these assumptions. Actually, we won't be asked for the assumption, but you need to know them. Why? Because usually when you use a regression model to represent the relationship between the variables, of course you will be doing this by using a software. In a software, the first step you need to do is to take your data set and do what we call a residual plot. The residual plot will show you this. Okay, that the assumptions are fulfilled. This is one way. And the residual plot plots the different values of the arrows. طبعا cannot be calculated manually. This is a hassle. That's why we use software. It's a hassle يعني. But let's talk about what are the main assumptions of a simple linear regression model. First, the relationship between x and y should be on the average linear relationship, and this is what you can see from the scatter plot. Okay. The values of x and y are not random. For every x, I have a value for y. Okay, and it has no probability on it. The only value that changes are the errors. So the errors are the random values. According to the values of the errors, we do the residual plot and check for the different assumptions. So the errors are random variables that are independent, okay, that are normally distributed with the mean of 0, and they have constant variance. Okay, so basically these are the main important assumptions, which are the assumptions concerning the errors. Okay, they are independent, normally distributed, the mean of 0 and constant variance. The plot of the residuals highlight these assumptions. Okay, so what happens when I want to check from my data set if the assumptions concerning the residuals are fulfilled? Because if they are fulfilled, the rest are fulfilled. So I will check for the first one for the linearity for the scatter plot, and then I will ask my software to do what we call the residual plot. If it looks like this plot show randomness. Okay, the line in the middle represents the mean, and since the values are equally distributed, okay, below and above this line, okay. So this is a typical residual plot that show randomness of the errors. Now let's look at another one. If you look in here, the line in the middle that represents the mean, but the values are not, or the points, the errors are they don't have equal values, they are not distributed with the same pattern below and above the line. So this is not constant variance, which means that the assumptions are not fulfilled, so we cannot use the regression to represent the relation between the two variables. Yani basically residual plots are used to check on if the assumptions are fulfilled or not. If the assumptions concerning the residual are fulfilled, we go on with the residual model, we look at the line and all of this stuff. But if residual plots are not, don't show that the assumptions are fulfilled, this means that you cannot use the regression models to represent the data sets you have. Okay, this is another figure. If you look in here, you will find that the points are not equally distributed. So actually, it doesn't look like linear. It is a non-linear relationship, so I cannot use linear regression to represent it. Hello everyone. Sorry, hello everyone. So let's continue talking about regression model. The last part we have for regression, for the simple linear regression model, is how to assess the linear regression model. So the regression equation or the regression model used can be assessed by two tools or two ways. We have what we call the coefficient of determination. We're going to talk about it in a moment. Or we can use ANOVA table. If you remember the ANOVA that you took before, will be used as an assessment tool also. Now, for us, we can talk about the coefficient of determination. طيب we have a couple of slides that you can skip. You can read if you want, but anyway, you can skip this one. And we move to this one, which is still you can skip it. It talks about the coefficient of determination. How is it calculated? Still you are not asked to calculate it. You simply need to know a simple way to calculate it. Actually, if you are given, like in the example for the triple A construction, you are given R, which is the coefficient of correlation, as 0.83. Remember, we said we can use this to judge the relation. It is positive and strong. From R, I can calculate the coefficient of determination, which is called R squared. So this R squared, which is capital R squared, is what is called the coefficient of determination. How do we calculate this? You calculate this by squaring the value of small r. So the coefficient of determination is equal to the square of the correlation coefficients. Now, what is this coefficient of determination? What does it measure exactly? The coefficient of determination measures the proportion of variability in y that is explained by the regression equation. Now, what is meant by this? If you remember, we said on the scatter diagram, when you plot the points and then when you find the equation of the regression line and you draw it on the scatter diagram, you will find that some points are on the line and some points are not. Some points are below or above. Actually, the coefficient of determination will give us an indication of what is the proportion of the points that are on the line. So basically, we say that this coefficient can help me to assess my line of regression. Yani, in other words, in this example, for example, R squared is approximately equal to 69% or 0.69. This means كده as a summary أو if I want the imager to think about it as an image, and then we're going to talk about the exact interpretation. So it's like saying that 69% of the points on the scatter diagram are on the line. 69% of the points okay, are on the line. Of course, this is an indication of a good line. This line is good. If r squared is equal to 85, 0.85, this means that 85% of the points on the scatter plot are represented on the line. On the other hand, if r squared was equal to 32%, so this means that 32% of the points are represented by the line. So this means that this line is not that good, of course. It is simply used to explain 32% or 39% of the values. But if it's 69, like in our example here, this means that this line can explain or can show 69% of the changes that happen in Y out of the points that show on my scatter diagram, in other words, which means that this is a good line. It's not bad. So let's go to look at what is the best interpretation for R squared. In our example, R squared is about 69%. So we can simply say that about 69% of the changes or the variations in the company sales, which is in Y is the company sales. Yeah, in general, let's start with what is the general interpretation of R squared, or the general definition of the coefficient of determination. The coefficient of determination shows us the percent of changes or of variations in Y, اللي هي dependent variable, that are explained by the changes in how the variations in the values of the independent variable, which is x. So let's go to our example in the AAA construction company, in which we were talking about the relation between the sales of the company and the payroll. When R squared is equal to 69%, you're going to say that about 69% of the changes or variations in the company sales is explained by the changes or variations in the payroll. Okay, so as we said, we have another way to do the assessment, which is ANOVA table. Okay, and I will skip this. This is simply a full explanation of the different values that you need to put in an ANOVA, which you are not asked to do still. So let's move to what are we going to do? How are we going to test for the significance of the model? Now, so we'll go back to the basic equation in which we're going to talk about y equals to beta naught plus beta 1x plus epsilon. Okay, this equation is to be used to represent the relationship between x and y, or between the two variables, if we have population data. Now the issue is that usually the data you have, as in the example we stated, are sample data. That's why we have to estimate the equation. That's why it was called or denoted by y hat equals to b naught plus b1x. Now we're going to go back to b naught is used to estimate beta naught, and b1 is used to estimate beta 1. And we're not going to do any estimations, simply calculated b naught and b1, and we know b naught and b1, and we're going to use these values to test the significance of the relation. Now, when is this relation significant? If the value of beta 1 is significant, which means that if beta 1 is not equal to 0. If beta 1 is equal to 0, this means that there is no relation between x and y, of course. If it's not equal to 0, this means that this relation exists and is a significant one. So how are we going to do this test? Usually to do a test, you need to define your two hypotheses, the null and alternative hypothesis. Now, our null hypothesis will be in this case that beta 1 is equal to 0. Beta 1 equal to 0, which means that there is no linear relationship between x and y. Okay? If there is no relation, it means that the relation is not significant. H1 is beta 1 is not equal to 0, of course, which means that there is a linear relationship between x and y, or in other words, the relation is significant. So what we're going to do in this part is, after checking with the coefficient of determination, how good is the line that we have predicted, okay? So now this line is a good line. It's not because it explains a large proportion of variations in y due to changes in x, or is not good because it explains a small proportion of variation in y when x changes, and so on. After that, we need to use this line that is used to represent the relation in the sample to talk about the population. Now, based on this equation we have, can we say that this line can be generalized on the population and it will represent a significant line or a significant relation between x and y in general, yes or no? So now we need to compose a hypothesis test. So we define our null hypothesis as being beta 1, which is the slope equal to 0, which means that if this is acceptable, there is no linear relationship between x and y, or in other words, the relation is not significant. Yani the relation represents simply the data represented in the sample, but it cannot be generalized on the population and say this is a significant relation that can be used on the whole population. This is what is meant by that. Now, the alternative hypothesis, on the other hand, which is the hypothesis that we accept if H1 is rejected, will be beta 1 is not equal to 0. So if beta 1 is not equal to 0, so there is a coefficient for x, which means that the relation between x and y is a significant one, or there is, in other words, there is a relation between x and y. Now, how do we do this? The values are plotted in ANOVA table. So if you remember the components of ANOVA table, in the first column we put the factor, which is in this case the regression line, and then the residual or the error, and then we put the total. Second column we put the sum of squares. The third one, the degrees of freedom. You divide the sum of squares by the degrees of freedom to get the variance. So it is the mean square, which is the variance. You divide the two variances to get the value of f. You compare it to f from the tables to take the decision, or since we are using software, we'll be relying on the p-value, which is in the column here called significance. What is meant by significance is the p-value. So you compare the p-value to alpha and you take your decision. Now let's look at our example, and this is typically what you're gonna have. So let's see if I have the data for the AAA construction company and I was given this output. How can I use this output to answer several questions? First of all, okay, if you look at the ANOVA table you have here, look at the square, okay, that is marked in red. It is written significance f. This significance is the value of what we call the p-value. A small reminder about what is the p-value. The p-value is a value that you can read and usually can use it to take your decision when you do a hypothesis testing. You compare p to alpha. If p is smaller than alpha, yani p is smaller than the level of significance, we reject the null hypothesis. In other words, we accept the alternative one. If the p-value is larger than the level of significance, we accept the null hypothesis and reject the alternative one. In our example, the p-value here is equal to 0.0394 and alpha is equal to 0.05. So I'm comparing these two values, you will find that the p-value is smaller than alpha, which means that we will be rejecting the null hypothesis. In other words, accepting the alternative one. The alternative one says that beta 1 is not equal to 0, which means that there is a linear relationship between x and y, or in other words, the regression line or the relation is significant. Okay, and this is what you will be asked to do. You will be given an output like this, and from this output you can answer several questions, as I said before. So if you are asked to assess or to test the significance of the relation, you will look at the part titled as ANOVA, اللي هي الأنوفا table. What concerns us in this table is the last column, اللي هي significance, which is the p-value. So you will take the value given there, compare it to alpha. If it's smaller than alpha, like the case we have in this example, you reject the null hypothesis, which means that you accept the alternative one, and you will say that the relation is a significant one. If the p-value is larger than alpha, you will say that we accept the null hypothesis, rejecting rejecting the alternative one, sorry. So this means that there is no, or the relationship, in other words, is not significant, or there is no relationship between x and y. What else can we see from this output? You will find that you can have r squared, which is the coefficient of determination, which, as we said before, is 0.69. So now from the output still I can get the value of r squared and say that 69% of the changes in the company sales are explained by the changes in the payroll. Okay, so looking at the output, and sometimes in the output also we can find the value of the coefficient of correlation.